Good morning, class.
Morning.
Good morning.
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 Good morning.
Morning.
Good morning.
Morning.
I can see you're already 114 class, so we'll start immediately. Because basically the initial part of the lesson, we are going to review what you learned in the previous lesson with Mr. Momani, just to polish up and find out if you got the concept. And if not, we top up on that where necessary. So the topic we are going to cover is radioactivity as shown on the screen. Can you see my screen? Can you see what I'm sharing?
Yes.
Yes.
And can you hear me clearly?
Yes.
Yes, we can.
Yes, we can.
Good. So the topic is radioactivity. I'm Madam Eddah Hamisi. I teach chemistry and another subject which I don't need to talk about now. So the first thing we look at when you talk about radioactivity is the stability of nuclides. I'm sharing page 1 of the content. I hope it's all legible. Are you seeing what I'm sharing?
Yes.
Okay. So stability of nuclides, we start by defining a nuclide, which I remember Walimu discussed with you. I remember somebody asking, what do you mean by a nuclide? So right there, you can see a nuclide is defined clearly. It is a distinct nucleus, which is characterized by a specific number of protons and neutrons. So earlier on in Form 2, we learned about the structure of the atom. And we said the atom has a central part known as the nucleus. And then we have regions surrounding the nucleus that are known as the energy levels. We also mentioned that there are 3 types of subatomic particles. Which are the 3 types of subatomic particles? Somebody?
Protons, electrons, protons, and neutrons.
We have electrons, protons, and neutrons, correct. Of these 3, which ones are found in the nucleus?
Protons and neutrons.
Protons and neutrons are found in the nucleus. So if we take a proton and narrow down to the nucleus, so that we are now looking at the number of protons in the nucleus and the number of neutrons in the nucleus, then we now talk of a nuclide. So a nuclide is just a nucleus, bearing in mind the number of protons it has and the number of neutrons it has. We have 2 examples there. We have carbon, the letter C, which is the symbol for carbon. So the symbol for the nucleus is the same as the symbol for the atom. It's only that when now I write C612, you bear in mind that I'm talking about the nucleus. I'm referring to the carbon atom nucleus and not the whole carbon atom. So looking at that C, and then 6, then 12 up, what does that mean? How many protons does it have? How many neutrons does it have? You raise your hand when you want to answer. The first nuclide there. How many neutrons does it have? How many protons does it have? Yes, Enoch Mugeli. Yeah. Enoch, we didn't hear you. Somebody else? Or Enoch here? There must be a problem with Enoch's mic. Yes, Shadrach Kipruto.
So for the carbon, it has 6 protons and 6 electrons. 6 protons and 6 neutrons.
Correct. Just continue on to the second one. How many neutrons and how many protons?
The second one has 6 protons and 8 neutrons.
Correct. The second one has 6 protons and 8 neutrons. So what you should bear in mind, as I've represented these, the C612, C614, I'm not picturing the atom. I'm picturing only the nucleus. Now, the next thing is about stability of nuclides, which you discussed, and you're told that this depends on the neutron-proton ratio. And a neutron-proton ratio of 1:1 for the small nuclides shows that they are stable. An example is given there of calcium with 20 protons and 20 neutrons. Therefore, the neutron-proton ratio is 1:1. Then we need to note that as nuclides become larger, the number of neutrons increases. And this is due to the fact that we know that the protons have similar charge. What is the charge of a proton? What is the charge of a proton? Protons, are they negatively charged or positively charged?
Positively charged.
They are positively charged. So protons are positively charged, and they are found in the nucleus, a very small region. All of them are positively charged. And we know that like charges repel and like charges attract. So when we have very many protons in the small region of the nucleus and all of them are positively charged, they'll be repelling each other. As a result, the larger the number of protons, the more neutrons needed for the nucleus to remain stable. So we have an example there of lead 208, which has 82 protons. And how many neutrons does it have? If you can see what I'm sharing. How many neutrons are there in the lead 208, given as an example there? How many neutrons? Yes, Arnold?
126.
Very good. So if you go ahead to calculate the neutron-proton ratio, you find that it's about 1.54:1. So this is still stable. But you are told that when the neutron-proton ratio increases until it reaches about 1.6:1, then the nuclide becomes unstable. So we are told a neutron-proton ratio ranging between 1:1 to 1.6:1 is where we'll find the stable nuclides. And we refer to this as the band of stability. So the range between 1:1 to 1.6:1 approximately constitutes a band of stability within which stable nuclides lie. So if you look at my screen there, we have a graph. On the vertical axis, we have number of neutrons. On the horizontal axis, we have number of protons. And then we have the lower straight line is the line where the neutron-proton ratio is 1:1, meaning if there are 10 neutrons, there are 10 protons. If there are 60 neutrons, there are 60 protons. Then the upper line is the line where the neutron-proton ratio is 1.6:1. So, and then the band you are seeing, the band that is in between there is what we refer to as the band of stability. So inside there, we have plotted the number of neutrons and protons for actual nuclides, and these ones are those that are stable. I know that we say approximately because you can see there are some plots that are above the line 1.6:1, and those the plots there are for nuclides that are stable. So that is why we have to say approximately. Radioactivity is a very complex process, and the scientists are still studying it so that they can actually understand what is the basis, what goes on in radioactivity. So there's still a lot to learn, and there's room for nuclear scientists. I hope this class will motivate somebody to become a nuclear scientist in the future. So yes, that is where we are. Any questions up to that point? Yes, Noel?
So when you say that there's a repulsion between the protons, so it means that it is that repulsion which causes the instability.
Exactly. It is that repulsion that causes the instability. Very good. Any other points to add or to ask? about? Yes, Levins? Levins,
I'm asking
you've got it, yeah? Yes.
if the ratio of neutrons to protons is 1.7 to 1, that is unstable.
Yeah, that will be unstable. That will be unstable. But then again, note that we say approximately, meaning there'll be exceptions to the rule. But generally, most stable nuclides have their neutron-proton ratios ranging from 1 to 1 to 1.6 to 1. Yes, Noel?
This statement down here that nuclides with more than 83 protons are unstable regardless of the neutron-proton ratio. So if a nuclide has maybe 90 protons and the neutron-proton ratio is maybe 1:1, it is still unstable.
Very good. We had not gotten there, but you've taken us there, and it's true the way you've explained. If a nuclide has more than 83 protons, it doesn't matter whether the neutron-proton ratio is 1 to 1, it will be unstable. And that takes us back to why I insist approximately constitutes and not just constitutes. So as such, there are actually two indicators. I would not want to call them factors, but you may find somebody asking you about factors, but they mean the indicators. Indicators of stability of nuclides. We have two. One is the neutron-proton ratio, and the second one is the number of protons. What term is used to refer to number of protons? Kutoka Form 2, Term 1. I think you even did it in Form 1. Tukona, what do you call the number of protons in the nucleus of an atom inakuwa described now which term? Yes, Karani?
Atomic number.
Very good. So there are two indicators of stability of nuclides. One, the neutron-proton ratio, and two, the atomic number. We move on?
Yes.
Good.
Yes.
So then you went ahead and defined radioactivity. The definition remains, is only that now I've written it and I'm able to share my screen. I like the last lesson, I had issues. So the process is there. Then we have radioactive decay there, defined, radioisotopes and isotopes which are radioactive. And then radioactivity is said to be a nuclear reaction and not a chemical reactions. And those factors there you discussed with Mwalimu in the previous lesson. Unless there's anything you need me to highlight, I'll just move on. Anything you need me to discuss further about that? Okay, it seems you're comfortable. Then you went ahead and mentioned the types of radioactivity. There are two types, natural radioactivity and artificial radioactivity, as discussed with Mwalimu in the previous lesson. Then we have types of radiation. At our level, in our syllabus, we discussed 3 types of radiations. Somebody named the 3. 2 are showing on the screen, but I just want to hear a voice. One of you boys naming for me the types of radiations you discussed with Mwalimu. Yes, Raymond?
Alpha, beta.
We have alpha, beta, and gamma. So just a quick review. Alpha zinaitwa alpha particles. The symbol is clear from what I'm sharing. And you learned that they are positively charged helium nuclei ejected from the nucleus. Remember, tumesema radioactivity is about the nucleus. When the nucleus is unstable, radioactivity happens. And one way in which radioactivity happens is by ejecting a helium nuclide or nucleus. And what is that? It is just comprised of 2 protons and 2 electrons. So I want you to get this clearly. When I say a helium, it's just simply 2 protons and 2 neutrons. That forms a helium nucleus. See how it is represented there. We have He2, number of protons. 4 is the mass number. So if the number of protons is 2, the mass number is 4, it means that the number of neutrons is 2. So a helium or an alpha particle is just 2 protons and 2 neutrons. Alafu zimeshikana pamoja. Zimepoma particle inaitwa alpha particle. In equations, they are represented using He24. And note that there is a charge there, 2 positive. I'd like somebody to explain for us these 2 positive charge inatoka wapi? Any reactions? Why do you think we've indicated that the charge is 2 positive? Two positive charge in the alpha particle, where is it coming from? Any ideas?
It does not contain electrons.
Yeah, come up again.
Can we say that it doesn't have electrons?
Of course, it doesn't have electrons. Remember, tumesema imetoka kwa nucleus. Don't think in terms of the helium atom. You know that the helium atom is stable. It has a stable duplet configuration. Atuongei juu ya helium atom. Hapa tuko tu na nucleus, imetoa 2 protons, imetoa 2 neutrons, imeshikana. When the meshikana zinaitwa alpha particle. So it has the 2 positive charge because it's so simple. I would have expected somebody to say it. BCS, Brian, why does it have the charge of 2 positive? BC, you've disappeared. So yes, Noel?
Would it because of the 2 protons?
Exactly. An alpha particle is made up of what? 2 protons and 2 neutrons. What is the charge of neutrons? 0. What is the charge of protons? 2. Since there are 2 protons, the charge becomes 2 positive. So the electrical charge is 2 positive, and you're told it's the heaviest type of radiation particle. Then the other one is the beta particle. Beta particle, it's interesting. They are negatively charged. They're actually electrons, but we say that they are negatively charged fast-moving electrons. And what's important to note is that they are ejected from the nucleus. They do not come from the energy levels. They come from where? From the nucleus. And how are they formed? They are formed when a neutron changes into a proton. You see how interesting that is? When a neutron changes into a proton, an electron is formed. Quite interesting. And that electron, when it is formed in the nucleus there, it is ejected inarushwa nje. So inatoka kama a beta particle. We call it a beta particle. So a beta particle is a fast-moving electron ejected from the nucleus when a neutron changes into a proton. Take note of the equation there. You should be conversant with it. We have a neutron 0, 1 changes into a proton 1, 1, and in the event, an electron is formed. That electron that is formed is what we are calling a beta particle. So they have an electrical charge of 1 negative. Then the gamma rays, we have, they're unlike beta and alpha radiations, they're not particles, they're just energy. They have no mass and they have no electrical charge. Take note of the symbols we use for the 3 types of radiations: alpha in red, beta in blue, and gamma in green. Note that alpha and beta are particles, and then we talk of gamma rays. Up to that point, clarification, addition, subtraction. Yes, Levins?
Can you pardon the equations?
The equation for the formation of a beta particle?
Yes.
Yeah, it's right there. So we are saying a beta particle is formed when a neutron changes into a proton. A neutron is found in the nucleus. A neutron can change into a proton. When a neutron changes into a proton, it forms an electron also. The N is for neutron, 0 atomic number, meaning it has no protons. 1 is the mass number. The 1 neutron plus 0 protons gives you a mass number of 1. The proton that is formed, atomic number is 1. That is the number of protons. The mass number is also 1 because mass number is number of neutrons plus number of protons, nani proton peke yake. So its mass number is 1. Then an electron, you can see how it is represented. What in the position where we usually have atomic number, there's a -1. Where we have a mass number, there's a 0. But there's something I need to clarify here. The -1 that is used in the representation of an electron is not actually the mass number, is not the atomic number. It's the electrical charge. So note that the -1, this -1 here is not atomic number of the electron. It is the electrical charge. Is that okay now?
Yes, thank you.
Good. Then we move on to somebody else? Okay. We move on to properties of radiation. We are required to discuss only 3 in our syllabus. There's penetrating power, there's ionizing effect, and then there's deflection in an electrical field. These you already discussed with your teacher a bit, but we're just going to go through. Penetrating power. We use 3 substances or items, for lack of a better word, to test or to see the differences in the penetrating power of the 3 types of radiation. We have a sheet of paper, we have aluminum foil, and we have a lead block. We are considering which one is going to pass through the 3 and which one will be stopped by the 3. So there I've indicated stopped by. So an alpha particle will be stopped by a sheet of paper. But both beta particle and gamma rays will pass through a sheet of paper. Then aluminum foil. The beta particle, which manages to pass through a sheet of paper, is stopped by aluminum foil. The gamma rays bado zinapita aluminum foil. Then lastly, a lead block. The gamma rays pass through a sheet of paper, pass through aluminum foil, but are stopped by a lead block. So from that discussion, which of the 3 radiation has the lowest penetrating power? Class.
Alpha particles.
Alpha particles.
Alpha particles.
Very good. Alpha particles have the lowest penetrating power. Mpaka zinastopiwa na paper. In other words, if you put a piece of paper in the way of an alpha particle, haitapita. A piece of paper will be enough to protect you from an alpha particle. But aluminum, but the beta particle will pass and get to you. For you to protect yourself against contact with beta particle, utashika aluminum foil. Do we know aluminum foil? Tunajua
Yes,
aluminum
yes.
foil? Yeah.
Yes.
So if you put aluminum foil in front of your face, if a beta particle had been released and it was approaching you, you place the aluminum foil in front of you, haitapita, you'll be safe. But for gamma rays, you need to look for a lead block. Hope that is clear. Then here I have a diagram. Actually have a diagram. You see the paper, we have the aluminum foil, you have the lead, and that tumeleta concrete to spice it up. So we have alpha particle stopped by a sheet of paper. If it's stopped by a sheet of paper, do you think it will pass through aluminum foil?
No.
No. So
No.
it is stopped by all the 4 there. Alpha particle is stopped by paper, will be stopped by aluminum, will be stopped by lead, will be stopped by concrete. Then when you come to beta particle, it apenya through karatasi, but aluminum foil, it will not be able to pass through. And that means it will also not be able to pass through lead block or even concrete. Gamma rays passes through paper, passes through aluminum foil, but is stopped by a lead block. A neutron, just for fun, know that that one will pass through paper, pass through lead, will only be stopped by concrete. The next property is deflection by an electric field. We already noted that alpha particles are the heaviest and they are positively charged. And I already mentioned, and we all know that like charges repel and like charges attract. So a negatively charged particle will be attracted to the positive plate. A positively charged particle will be attracted to the negative plate. How much it's deflected depends on the mass. So alpha particles, since they're positively charged, will be deflected towards the negative plate. You can see from the diagram that I'm sharing, they're deflected towards the negative plate. Beta particles are negatively charged. They're deflected towards the positive plate. Gamma rays have no charge, and therefore they are not deflected by an electric field. I want you to compare the deflection in beta and alpha. What can you comment? What comment can you make about deflection in beta and alpha, apart from the fact that beta particles are deflected towards the positive plate and then alpha particles towards the negative plate? Any other comment you can make?
Beta particles are deflected further than alpha particles.
Very good. Why do you think this is so?
Because
Alpha particles are heavier.
Due to the weight of the particles.
Yeah, you need to be specific due to the weight, as it be specific. Due to the weight, then some more.
Electrons.
Because the beta particle is lighter than the alpha particle. So you just don't say due to the weight, you have to specify what about the weight? The fact that the alpha particles are heavier than the beta particles, they are less deflected in an electric field. Last but not least, ionizing effect. Ionizing effect, what do you understand by the term ionizing effect? What do you think that means? Derek? Oh, Derek, your mic is just off. Any ideas about what we mean by ionizing effect? We know what ions are. So when I say ionizing effect, what comes to mind?
Ability to ionize particles.
Very good. And how are particles ionized? How are particles ionized? By removing which subatomic particle from their atoms?
Electrons.
Very good. So ionizing effects, these three radiations, alpha, beta, and gamma, have enough energy to cause electrons to detach from atoms in substances or even in molecules. So when that happens, the atoms turn into ions, and that is why we are talking about ionizing effect. I used a bit of maths here. Maths is the second subject I teach. The way I've indicated using the inequality signs, can somebody read out for us how we would read that statement? How would we read that statement where we have the symbols for alpha, beta, and gamma? I'm borrowing from mathematics. I hope I'm not making anybody's life hard. Yes? Who can tell us what that means? Yes? Who's speaking? Yes, Michael Karanja.
So we can see that the alpha particle has a higher ionizing effect than the beta, and the beta has a higher ionizing effect
than the gamma. Very good. So that is what that statement means. The symbol I've written there means greater than, yeah? Like alpha is greater than beta, beta is greater than gamma. So the one with the highest ionizing effect is alpha particles, and this is due to two factors. The first one is its slow speed. Alpha particle moves slowly at a slow speed. And then the second factor that causes it to have the highest ionizing effect is its high charge. So if you are to be asked what factors causes the alpha particles to have the highest ionizing effect, talk about slow speed and talk about high charge. Why is the slow speed important? Instead of just passing through once, it goes slowly, meaning that whatever ionizing effect it will have enough time to ionize the atoms that it is coming into contact with. So simply put, the slow speed and high charge of alpha particles causes them to have the highest ionizing effect. Up to that point, any further clarifications? Any clarifications up to that point? Okay, just a wrap up. So which are the three properties of radiations we can use to distinguish between them from class? Which are the three properties of radiations that can be used to distinguish between them? The three. Yes, Brian Ganga?
The first one is the penetrating power, deflection by an field, and ionizing.
Very good. And under penetrating power, what three items do we use to test? What three items do we use to? Yes, Jonathan?
A sheet of paper, aluminum foil, and a lead block.
Very good. Of the three radiations, which one is only stopped by a lead block?
Gamma.
Yes, Nimrod?
Gamma.
Gamma is the one that is stopped by a lead block only. Very good. Radioactive decay and half-life. So radioactive decay rates are measured in half-lives. A half-life you went through with Mwalimu. It is the time taken for a given mass or number of radioactive nuclides to decay to half the original mass or number. And this half-life is constant for a particular nuclide, and the symbol of half-life is T half. Note the T half there, I hope you can see it. This is the symbol for half-life. So if you see T half, know that we are referring to half-life. So different radioactive nuclides have varying half-lives. Lithium-8, very short, 0.838 seconds. Iodine-131, if you are seeing the table, what is the half-life of iodine-131?
8 days.
It is 8 days. What does that mean? It means if you had 20 grams of iodine-131, after 8 days, itakuwa imebaki 10 grams. Half of the amount you have would have decayed after 8 days. Uranium-235, what is the half-life?
703 million years.
Just look at that. Iodine-131 need 8 days. So 20 grams, 10 grams will remain after 8 days. Uranium-235. If you have 20 grams of uranium-235, it will take 703 million years for 10 grams to remain. Sounds quite weird, but that is the truth. So different nuclides have different half-lives, where half-life is the time taken for a given mass or number of radioactive nuclides to decay to half the original mass or number. When we plot the remaining amount of a radioactive nuclide against time, Then we come up with a curve known as a decay curve. So a decay curve is a graph of remaining amount of radioactive nuclides against time. So I have two examples there, cobalt 60 and that for iodine 131. So on the vertical axis, you have cobalt 60 remaining. We have it in percentage. You can have the actual grams or the actual mass in grams or the percentage. So in this case, we have the percentage. And then on the horizontal axis, we have the number of half-lives. So in this decay curve, you will start with at time 0, you have 100%. So our first plot is 0, 100. And then after the first half-life, the percentage remaining would be 50%. If you had masses, if you had 10 grams at time 0, after the first half-life, the mass remaining would be 5 grams. Then after the second half-life, at 2, we have the 50% again reducing to half of 50%, which is 25%. And then after the next one, the 25% reduces to 12.5 and so on. So when you plot a graph of remaining amount against time, then what you come up with is a decay curve. At the end of the lesson, I'll give you some data, which you'll go ahead and draw a decay curve for. And it's just a, yes.
It's just a quick roll call. Sorry for
Yeah.
that.
Okay.
So students, just take a roll call. Look at your screen, confirm your class quickly. Should take you less than 5 seconds.
We were called for, actually I will still end up there.
We can do it fast enough. Joshua says you can't see his, okay.
I also can't see mine.
You can see. It could be you have old versions of Zoom. You may need to update that. Because if you have over 87% of you seeing, and I can see a number missing, maybe you may need to update that. Okay, 212. We're about 40 boys. At 2:15, we still have a number. Please, it takes you less than 5 seconds. Just click on it if you can see it. Those who can't see it, I'll handle that. Okay, done. Malim, you can proceed. Thank you so much. If it says error, it means your network, but it's okay. Go ahead, madam. Thank you so much.
Are we through with the roll call? Okay.
Yes.
Yes.
Sawa. So decay curve, remaining amount, vertical axis, time on the horizontal axis. You draw a smooth curve through the points, but ensure that it does not touch the horizontal axis. Then now we have questions on radioactivity. This you already did with Mwalimu. So it's just a review. Yes?
Can I ask a little question about the uranium-235 and its half-life?
Yes.
Being
yes.
700 years. How exactly is it calculated? Because nobody has lived that long. Or how exactly do they calculate that?
Very good question. We do not have to live to 703 million years. Like, so let's say you had the 20 grams of uranium, like maybe in 10 years, you get the amount, or you get the amount that has like decayed. Then you can calculate how long it would take for that original amount to decay to half. Then you project that to 703 million years. So you actually do not have to wait for 703 million years. Very good question. Are you answered?
So that means that it decays at a regular rate.
Regular in what sense?
Because maybe after 10 years, the rate at which it decays will maybe triple or go 10 times faster.
I'm not sure I get that.
Madam, I think
Triple. Yeah.
I think saying
he means at a constant rate.
The rate is not actually constant. If the rate was constant, we'd get a straight line. Okay. The rate is not constant. Okay, what can you say about the rate? Looking at the shape of the curve, borrowing from your maths, is the rate decreasing? It's definitely not constant. If it were constant, we'd get a straight line. Is the rate decreasing or increasing?
Decrease.
The rate is actually decreasing. Okay, let me just use a whiteboard, but this will mess me up. Okay, no, that will, okay, the rate is actually, let me just try to explain orally. Let's say you have 20 grams of the, let's use something that has a short half-life, the iodine-131, which is 8 days. So after 8 days, the mass reduces from 20 grams to 10 grams. Okay. So in the first 8 days, how many grams have decayed? 10 grams. Are we in agreement?
yes.
Then the next half-life will also be 8 days, but the 10 grams will decay to how many grams?
5.
Will decay until only 5 grams remain. So in the second half-life, how many grams have decayed? Tumetoka 10 grams, tumefika 5 grams. How many grams have decayed?
5 grams.
5 grams. So note that in the first half-life, 10 grams decayed in 8 days. In the second half-life, 5 grams decayed in the same 8 days. So you can see that the rate of decay is actually decreasing. Is that okay? Yeah.
Yes, very much.
So I don't know whether the person who had the question is answered. Was that, please, are we okay now?
Not really.
Yes, just feel free. Just come up again. At what point do you have an issue?
No, like in that example, so after it has gone from 20 grams to 10 grams, the first half, the second half-life from 10 to 5 within the same 8 years. Now, for like uranium-235, which takes such a long time, maybe assuming at some point it goes from maybe 10 grams to 5 grams, maybe it will change from doing that in 8 days to maybe 12 days. Now that's what I'm asking, if there's a possibility of such a thing happening.
So that now the half-life changes or something like that?
Yes.
No, the half-life is a constant. Note that, please understand what half-life is. It's simply the number of the time taken for a given amount or number of nuclides to decay to half the original. The time taken for a given amount of radioactive nuclides to decay to half the original amount. So that is a constant. So meaning anytime the amount is halved, the time taken will be equal to the half-life, and it is constant for the particular nuclide. So you're intrigued with the uranium, which has a half-life of 700 million years. So what you are saying, if we had 10 grams of uranium, it will take that 700 and, is it 8 or 3 million years to decay to 5 grams. If you had 5, it will take the 703 or 8 million years to decay to 2.5 grams. So that remains constant. That time to decay to half the original amount remains constant. Yes? Are we okay now? Yes, Jonathan?
Why is the graph a curve?
The graph is a curve because the rate of decay is decreasing. The rate of decay is decreasing.
Should it be a straight line which is decreasing from the y-axis?
No, remember we start decreasing from the y-axis, starting from 0. Note that we are starting on the vertical axis, we have the amount remaining, or the amount of the radioactive nuclide. And we are seeing how that amount changes with time. So it is a decay. We are losing some of the nuclides. So the amount of nuclides is increasing as time goes by. So we have to start up and move down, and a curve, because this rate is decreasing it's decreasing, and the rate at which it's decreasing, it depends on the half-life. Some will be steep, some will be not so steep, depending on the size of the half-life. Okay.
And why should the curve not touch the horizontal axis?
Very good question. For that, I would like reactions from the students. Any ideas? Why shouldn't the curve touch the horizontal axis? Any reactions from class?
Because it never
yes, I have Ivan.
It never becomes 0.
Yeah, we will not have a case where the radioactive nuclide will decay until we have none. The amount can be very little, but never 0. Okay?
Yes.
Good. So now we have some questions here. This is also just a review. Those who are in class in the previous session should not have any trouble. We have first example, iodine 131 has a half-life of 8 days. If there are 200 grams of this sample, how much will remain after 32 days? So this one we just do simply. Initially you have 200 grams. And then you're asked, the half-life is 8 days. And we are asked how much will remain after 32 days. So the first thing you calculate is the number of half-lives. The number of half-lives will be equal to the time, total time for decay, divided by the size of one half-life, which in this case will give you 4 half-lives. Then you start to procedurally reduce the amount by half after every half-life. So we are starting with 200 grams. After the first half-life, 100 grams remain. After the second half-life, 50 grams remain. After the third half-life, 25 grams remain. And after the fourth half-life, 12.5 grams remain. So we stop after the fourth because we calculated and found that there are 4 half-lives. Then we have the second example. You can be asked about fractions. What fraction of a sample of sodium-24 will remain after decaying for 90 hours? The half-life of sodium-24 is 15 hours. So you start by calculating the number of half-lives. You get, in this case, there are 6 half-lives. Fraction, we start with a whole. A whole fraction is 1. So starting with 1, After the first half-life, 1 reduces to half. After the second, half reduces to a quarter. After the third, a quarter reduces to an eighth to a 16th. After the fourth, after the fifth, 1/16 reduces to 1/32. After the sixth, 1/32 reduces to 1/64. We stop after the sixth because we calculated and saw that the number of half-lives is 6. So we have more questions there. An isotope has a half-life of 5 hours. What percentage of a given mass of the isotope would be left after 25 hours? I want you to solve this question, number 3. Solve question 3. When you're done, you can just you can post your answer on the chat. I'm not seeing any answers. That's taking so long.
25%.
Yes.
3.1.
You can only send the chats to Ombiro.
Oh, you can only send to the host. Okay. So what are you getting?
3.125.
3.125.
3.125%.
3.125.
Okay.
3.125.
That is correct. And then we have, look at number 5. I want you to also attempt number 5. Number 5, it's the work. Okay, the work is done there.
You can send to Molim too. You can send to Molim, try sending again.
It's okay.
So number 5, it's upside down now. Q grams of a radioactive isotope takes 80 days to disintegrate to 7 grams. The T half of the isotope is 20 days. Find Q. Meaning we are looking for the original amount. Tumepewa time it took to decay, tumepewa half-life. We are told 7 grams remained after that number of days. So where did we start? So it's like we'll be going backwards. So again, as usual, always start by calculating the number of half-lives, unless of course you're asked for half-life. So number of half-lives, the total decay time, 80 days, and 1 half-life is 20 days. So you get the number of half-lives to be 4. But now you're starting from 7 grams. Look at how I've shown my work. I'm now starting from 7 grams. What remains after the decay period is 7 grams. Nimepata the number of half-lives, which led to this amount that is remaining is 4 half-lives. So nitasema 7 grams decayed from 14 grams. So going backwards, I double it to 14 grams. That is for the 4th half-life. The 14 grams, I double it to 28 for the 3rd half-life. The 28 grams, I double that to 26 for the 2nd half-life. Then lastly, the 56 grams, I double it to 112 for the 1st half-life. So the answer for this question becomes 112 grams. I remember we did this example again last session with Mwalimu, so it's just a review. So we continue. Determining half-life, I remember you doing with Mwalimu, so you don't have to do again unless somebody has issues. Like number 8, just to confirm that you're on the same page, I want you to work out number 8. 50 grams of radioactive was reduced to 6.25 after 45.5 days. Determine the half-life. Yes, Enoch Mugendi, you have a question? Please unmute and speak out.
My question is if there's a fixed formula of solving the equations we can use powers.
Sorry, we are not getting you clearly. Yes, Mr. Mumanyi, your hand is up.
Thank you, madam, for that wonderful presentation. But I want to make a clarification. There was a student there who was wondering about why is it that uranium-235 has 700 years as a half-life.
700 million, yes.
Yeah, 700 million as a half-life. So the student need to know that uranium has isotopes. We have uranium-235, uranium-238. The one that is the most abundant is 238, uranium-238. But also, students should know that we have what we call artificial radioactivity and natural radioactivity. Now, natural radioactivity is whereby now the radioactive substance undergoes decay on its own. But the artificial radioactivity, that one is now what we call forced radioactivity, whereby we said last time, you bombard the radioactive substance using a fast-moving neutron. Meaning that you can change the half-life of uranium by carrying out what you call what? Artificial radioactivity. Mostly remember uranium is used to manufacture atomic bombs. So you find that an atomic bomb can go off, or it just can undergo radioactivity within seconds. So meaning its half-life has been reduced by carrying out what? Artificial radioactivity. So you can reduce the half-life by just carrying out what you call artificial radioactivity. But if you allow uranium to decay on its own, it will take the 700 years on its own, naturally, on its own. It will take 700 years. But you can reduce the half-life by just bombarding it with a fast-moving neutron, meaning you are carrying out what you call artificial radioactivity. Then there was that thing of differentiating the alpha particle, beta particle, and gamma. The students should know that whenever you are told in an exam, draw a diagram to differentiate between alpha particle, beta particle, and gamma. Draw a diagram differentiating the three using a paper, using lead, and using aluminum foil. You must make sure, candidates, you draw the source of those radioactivity particles, and you must show the shield. You must show the shield when you're drawing, differentiating the three. Thank you, madam. Madam, I'm done. You can proceed.
Okay, thank you for that, Mwalimu. So we proceed. We were looking at number 8, where you are required to calculate the half-life. Let's work that out. As soon as you work it out, please post your answer so we can come to an agreement. I'm seeing one. Noel is giving 11.375 days. Are we getting the same answer? 15.17. 15.17, 15.17. So since we have 15.2, 15.17, somebody is saying they don't know how it's done at all, take us through, that is okay. Fine. Let us go through this. We have 50 grams. I'll use a whiteboard for this. So the question says 50 grams of radioactive was reduced to 6.25 grams after 45.5 days. Determine the half-life of that. So we'll do the procedural step at a time. We are starting with 50 grams. So at the start, we have 50 grams. Then it's reducing to 6.25 grams in 45.5 days. So we do the step by step. After the first T half, this amount would have reduced to half of 50, which is 25 grams. After the second T half, the 25 will reduce to half of 25. Somebody, what is a half of 25?
12.5.
So this is 12.5. Bado hatujafika 6.25. Remember tumeambiwa it will reduce to 6.25. So we continue, bado hatujafika 6.25. 12.5 after another T half will reduce to a half of 12.5. And what is a half of 12.5, boys?
6.25.
Will be 6.25. So we stop there because we are told the 50 grams reduced to 6.25 grams. So how many half-lives has it taken for the 50 grams to reduce to 6.25? You can see there's 1, 2, and 3 half-lives. Are we in agreement?
Yes.
Yes.
Then we were told the decay from 50 grams to 6.25 grams takes 45.5 days. This implies that the 3 half-lives are equal to 45.5 days. So we get 1 half-life. So we have 3 T halves is equal to the time we were told this decay took, 45.5. So what about 1 T half? 1 T half will be 45.5 divided by 3. What do we get?
15.1667.
So what are we getting?
15.1667 days.
Okay, that means therefore the correct answer is the 15.117. Are we now okay, Levins? Levins, are you okay now with the calculation, the working? Uko sawa. Sawa. Any other points of clarification?
Yeah.
Tuko sawa sasa. So we go back to that. Then I also want to bring to your attention that you can use a formula to calculate these, to do these calculations on half-life. The formula is indicated there, use of formula. The formula is remaining amount is equal to original amount times half to power n. Note that in this formula, we have n is the number of half-lives. N is the number of half-lives. So in example 19, I'm using the formula to calculate these. The half-life of a radioisotope is 29 days. What mass of a 92-gram sample will remain after 203 days? So let me again go back to the whiteboard and write step by step. So the formula is remaining amount is equal to the original amount times a half to power n, where n is the number of half-lives. So we are told to get what mass of 92-gram sample will remain after 203 days. So the first thing we do is to calculate the number of half-lives. Number of T-halves will be equal to the total time taken, which is 203 days, divided by the size of one half-life, which is 29 days. So this is equal to 7 half-lives. So we now just substitute in the formula. The remaining amount will be equal to original amount. What is the original amount? What is the original amount, boys?
92.
92 times a half to power 7. So that gives us 92 times 1 over 2 to power 7. What is 2 to power 7?
128.
128. So somebody evaluate for us 92 over 128. 92 divided by 128 becomes 0.71875. 7.875 grams. So hapo ni kutumia formula, very simple. All you need to have is the formula itself. Remaining amount is original amount times a half to power n. Know what this n means. N is not the total time for decay. N is the number of half-lives. So calculate the number of half-lives, substitute the details in the formula to get whichever part is asked for. That is okay. Please do not write on the screen unless asked to. Another example where we are using the formula. Number 10. A 250-gram sample of a radioactive bismuth-210 decayed to 31.25 grams in 15 days. Determine the half-life of bismuth-210, insisting again on use of formula so that we know both. In an exam situation, you are not limited to using a particular one. You'll use the one that you're comfortable with, but it's good to know both approaches. So we want to use the formula to calculate this. We will borrow a lot from maths in this case. Whiteboard, continue. So in this case, we do not know the half-life. We want to get the half-life. The formula still remains. Remaining amount is equal to original amount times a half to power n. In this case, we will not be able to calculate n because we do not know the size of the half-life. We have the total decay time is 15 days. Original amount tuko nayo, tuko na remaining amount. So the original amount is 250, remaining is 31.25. So you say 31.25 will be equal to the original amount, which is 250 times a half to power n. We do not know n. So we need to calculate n here. We'll divide both sides by 250. So we have 31.25 over 250. Somebody is playing around with the whiteboard. Patrick Mumo, I can actually see it's Patrick Mumo. Can you stop that? I hope you're concentrating as you're playing. Patrick Mumo, I don't need that in the class. So this will be equal to a half. We can change the half to decimal for easier calculation. We'll be using calculators there. Then we'll evaluate 31.25 over 250. Somebody calculate for us 31.25 over 250.
0.125.
So we have 0.125 is equal to 0.5 to power n. From your maths, if you have such an equation, what should you introduce for you to be able to get the value of n? What do you introduce? You introduce logs. So you have log 0.125 is equal to log 0.5 to power n. So you introduce logs on both sides. Now, this one, you have to remember your laws of logarithms. When multiplying, what do you do to the logs? When multiplying, what do you do to the logs?
Add the log.
Add. When dividing?
Subtract.
But in this case, we have powers. So with powers, you multiply. So what you should have is log 0.125 is equal to n log 0.5. So that means n will be equal to log 0.125 divided by log 0.5. Hiyo inakupea nini ukifinya kwa calculator?
3.
Inakupea 3. So n is equal to 3. Is 3 our final answer? Tumemaliza twende ama baada tujamaliza? Is 3 the answer to this question?
You have to repeat it.
No.
No. N is the number of half-lives, not the size of one half-life. We are asked for the size of one half-life. So we are told this takes 15 days. So that means 3 half-lives is 15 days. One half-life will be equal to 15 days, the total decay time, over the number of half-lives, which is 3. So one half-life is 5 days. So hapo ni kwa kutumia formula to calculate the size of half-life. A bit of maths there, but I hope you'll be comfortable with that. Any clarification on that? In an exam situation, if you're not comfortable with the formula, the progressive reducing or increasing of the masses gives you total marks. Do not stress yourself. But if you're comfortable with the formula, go ahead and use it. I think we are now okay, so we move on. So you can take a screenshot if you're able to. The workings are all there. then you'll be able to go through the workings and even do more practice. A note to take, we have a half-life, another way of defining half-life. I want somebody to read through that. I know we all know how to read. Somebody to read through that. Yes, Noel?
Half-life can also be defined as the time it takes for the count rate into bracket activity from a sample of the radioisotope to fall to half its initial level. Count rate is the number of decays per second recorded by a detector such as Geiger-Müller counter.
Geiger-Müller counter. So this is another way of defining half-life. In our syllabus, we are not required to know this definition, but what comes up is the fact that the questions on half-life can also be asked in relation to count rate, which is the activity. So a Geiger-Müller counter is just something like a watch, which will measure the rate at which a radioactive sample is emitting radiations. So we are not required to go into the details, but because in chemistry questions that involve count rate come up, I felt that it is proper to mention these. So now we look at a question that is talking about activity. Look at number 11. Look at number 11. A radioactive isotope has a half-life of 15 days and its initial count rate is 200 counts per second. Determine the count rate after 45 days. So the count rate is treated exactly the same way we treat remaining amount. So in this case, the first thing we'll do, as usual, can calculate the number of half-lives, which will be the total decay time, 45, and then the size of one half-life, which is 15. Somebody is asking me to pardon the definition. Back to the definition. Half-life is there. Can also be defined as the time it takes for the count rate, that is the activity, from a sample of the radioisotope to fall to half its initial level. What is count rate? It is the number of decays per second recorded by a detector such as a Geiger-Müller counter. And we have said that this is nothing to worry about. We are not required to go into details in our syllabus. A Geiger-Müller counter, just like a watch measures time, a Geiger-Müller counter will measure the rate of activity, the rate at which a radioisotope is emitting radiations. We are not required to go into details. So we are back to the question. So you are told the initial count rate is 200 counts per second. The half-life is 15 days. What will be the count rate after 45 days? So the number of half-lives is 45 over 15, which is equal to 3 half-lives. Then the way you reduce the mass is the same way you'll reduce the count rate. So initial count rate is 200, as I highlighted there. After the first half-life, the count rate reduces to 100 grams. After the second half-life, the count rate reduces to 50 grams. There was a bit of a mistyping there. So the count rate reduces, after the second half, the count rate reduces to 50 counts per second. And then after the third half-life, it reduces to 25 counts per second. So we stop at third half-life because you already calculated that the number of half-lives is 3. So your answer just becomes 25 counts per second. So the same way you use the mass in calculations regarding half-life, we use the count rate in the exact same way. So we have number 12 there. The activity of a radioactive lead-210 fell to 132 of its original activity after 10 years. Calculate its T-half. The T-half of hydrogen-3 and it is living, how long would this take? Yeah, I want you to do number 13. No, number 13 is not about count rate. But let's see, 14 had an initial of that. What would be the sample at which we have? Yeah, can you try number 14? Kindly try number 14 there and see if you are able to solve it. So you have a sample of cobalt 60, initial activity is 1,000 counts per second. What will be the activity of the sample after 15.6 years?
120.
The half-life is 5.2 years. Very fast, boys. Post your answer.
125.
125 is correct. Lennox 125.
125.
Ivo Doria 125. Ivo 2. So let it not start with you that what is this count rate about? So treat it the same way you treat the mass. So 125 counts per second is correct. So I don't know, you can take screenshots, or which method would you want us to get these, maybe these notes and the work, because there we have more questions there that I expect you to work on at your free time later on. Do we send to WhatsApp, or you can screenshot?
WhatsApp.
We send to WhatsApp.
WhatsApp. Yes,
Right,
madam.
Okay, that is okay. So we move on now to where we were actually to start today, but the technology messed us up. Nuclear reactions. So we already said that radioactivity is a nuclear reaction and not a chemical reaction. And since both are reactions, we write equations for them. And the equation for a nuclear reaction will indicate the change that is taking place in the nucleus, and in the process will indicate the radiation that has been emitted plus the new nuclide that is formed after the nuclear reaction. So we have grouped them into the three, according to the three radiations that are emitted. Whenever an alpha particle is emitted, we say that that is alpha decay. So we'll start by looking at how to write equations for alpha decay, where alpha decay just means a decay that occurs with the emission of an alpha particle. Then we have the beta decay, then lastly we have gamma decay. We know what an alpha particle is, and it's indicated there clearly. It consists of 2 protons and 2 neutrons. Note that what is undergoing the decay is the nucleus. Hatuna haja na hizi electrons zenye ziko kwa energy level. We are focused on the nucleus. So when a nucleus undergoes alpha decay, it emits an alpha particle, and an alpha particle is 2 protons and 2 neutrons. As such, there will be an effect on both the mass number and atomic number. Atomic number is the number of protons. The mass number is the number of the sum of protons and neutrons. So if we emit 2 protons, if we give away 2 protons and 2 neutrons, what will be the effect of the atomic number? Sorry for that. The atomic number will decrease by 2, and the mass number will decrease by 4. Example 1, we have Pacium 234, atomic number 91, mass number 234. When it undergoes alpha decay, it forms a nuclide in which the atomic number is less by 2 and the mass number is less by 4. So we have 91 minus 2, 91 there, minus 2 is what gives you 89. 234 minus 4 gives you 230. So the nuclide that is formed has an atomic number of 89 and a mass number of 230. Then the alpha particle is emitted. You also have to show the alpha particle as indicated there, symbol He, mass number 4, atomic number 2. So like that. The second example is not there. We are given the third. The third is now radium. Atomic number. What's the atomic number? I hope I'm not talking to myself. What is the atomic number of radium, class?
88.
88. What is the mass number?
226.
Very good. When a radium nuclide emits an alpha particle, atomic number reduces by 2. You can see the nuclide that is formed has an atomic number of 86. The mass number reduces by 4. You can see that the nuclide that is formed, which happens to be radon, has a mass number of 222. And then the helium, there was an omission there. The mass number and atomic number of helium must be shown. So you have 2 down for those who are writing and 4 up for the mass number must be shown. Usiandike tu He hivyo, andika He, atomic number 2, mass number 4, like that. Number 4 is there. I want you to attempt number 4. Hence come up with the atomic number of NP and mass number of NP and also number 5 there. As fast as you can, boys. When you're through, raise up your hands so you can tell us what is the atomic number and mass number of the daughter nuclide. We actually call that a daughter nuclide. Titus Kibi, what?
The mass number is 237 and the atomic number 93.
Very good. Number 5. So in number 4, mass number 237, that is the upper number. The lower number, atomic number, is 93. And number 5, faster. Yes, Samuel Abua, thorium.
The mass number is 90. The atomic number is 90, and then the mass number is 231.
Mass number is 230.
Hmm.
234.
234 is correct. 234.
Sorry.
So somebody is asking there, right? We have, why are the parent nuclides and daughter nuclides different from the floor? Why are they different? I don't know why you're saying different. Different in terms of the symbol or something like that. Because you know what determines a nucleus now, because we are narrowing down on a nucleus, what kind of nucleus it is the atomic number. Basically, it's just the atomic number. So one symbol, very good, is asking about the symbol. So in the first example, we have pacrium. The atomic number is 91. That is the parent nuclide. Then after alpha emission, the atomic number is becoming 89. Once the atomic number is different, it is no longer pacrium. The only nucleus that is said to be pacrium is that which has an atomic number of 91. And you know that atomic number is the number of protons. So if a nuclide has 91 protons, then it's pacrium. If it has 89, it is no longer that one. It's now something else, actinium, I think, AC. When you come to the example 3, radon ni ile nuclide iko na 88 protons. So if you see any nuclide iko na 88 protons, identify it as radon. So if after alpha emission, the atomic number is no longer 88, then it is no longer, this is radium. It's no longer radium. It now becomes Rn, which is radon. So you should know that what determines the identity of even an atom or even a nucleus is actually the atomic number. We look at the atomic number. Once they're different nuclides. I hope you're answered. Are you answered? We are unge. Then we go to beta decay. Thank you, Brian. Yes. Beta decay, we say that a neutron changes into a proton and emits an electron. A neutron changes into a proton and emits an electron. The atomic number of the parent nuclide therefore increases by 1 but the mass number does not change. I don't know whether we are getting this. A beta decay. A beta particle is emitted when a neutron changes into a proton and emits an electron. So as a result, the atomic number of the parent nuclide increases by 1. The mass number does not change. So in equations, you see how we represent. We have carbon 14, initially with an atomic number of 6. And then the mass number of 14. During beta decay, a proton changes into a neutron. So the number of protons increases. So initially we had 6, so that number will increase to 7 because a proton has changed into a neutron. But the mass number remains the same. So it was 14, it remains 14. Why? Mass number is the number of neutrons and protons. We just have a neutron changing into a proton. So the mass number is not affected. The sum of protons and neutrons is still the same. It's only that the number of protons is now 1 more than it initially was. So the mass number remains the same. Then we show that there is emission of a beta particle indicated as E-1, 0 for the superscript. Then radon 22688, beta decay, atomic number increases by 1, mass number remains the same, plus a beta particle. Then go on to number 3. Can you work out number 3 very fast? We have like 5 minutes. Okay. 5 minutes. Work out the atomic and mass number of copper. Atomic number of copper, Doria. Please indicate atomic number. Somebody is saying 29. And Doria is saying 29. I assume you're implying the atomic number. What about the mass number of copper? Okay. Mass number of copper, what will it be?
63.
The mass number remains to be 63. Good. Number 4, very fast. This one I want you to work out and even identify the symbol. Which nuclide is formed there? Identify the daughter nuclide. You should be able to identify it. Work out mass number, atomic number, and identify the daughter nuclide.
It's silicon.
Somebody is saying silicon. Silicon. What atomic number will be? 14. Mass number is 29. Are we in agreement?
Yes.
Yes.
Yeah. So basically, for the first 20 elements, you may be required to identify, but in most cases, will not give you questions that require you to identify the large nuclides like radon and actinium. You'll be given all the details. So you should not worry about mastering what is the daughter nuclide, rarely asked, unless maybe in this case where the nuclide that is formed is amongst the first 20. Atomic number is less than 20. Remember, you're required to master the first 20. Hydrogen, the first, and then the 20th is which one?
Calcium.
Yeah, calcium. So those ones you should be able to recognize. Lastly, just a statement, gamma decay, the atomic number and mass number do not change because the emission of gamma rays always accompanies other radioactive emissions and may or may not be shown in a nuclear equation. Note that we say we said that gamma rays are not particles. They are just pure energy. They have no mass number. They have no atomic number. They don't contain any protons or any neutrons. They're just energy. So they do not affect the atomic number or mass number. And rarely are they emitted on their own. They accompany other emissions. Like in the example we have there, I'm almost done, just wait. The example we have there, we have thorium, 230, 90, undergoing a certain type of decay. Which type of decay is thorium undergoing? Which type of decay is that?
Gamma decay.
Okay, both gamma and the one we can see HE is alpha decay. Atomic number reducing to 88, mass number to 226, alpha particle emitted, and in accompanying the alpha particle, there is also gamma rays. So the gamma rays that you can see I've indicated in equations will show a 0, 0, meaning no protons, no neutrons. It does not affect the mass and atomic number of the parent nuclide, simply accompanying the emission of an alpha particle in this equation. So it is exactly 10:45. If there are no other questions, if there is a question, I can clarify, but if there is none, we'll stop there for today. If you have a question, just unmute and ask. Yes, Titus, give you what? Noel? Okay. Seems
Okay,
no
my
questions,
question is,
okay. Yes.
Clarify why the mass number does not change in beta decay, please.
Okay. Note that in beta decay, a proton changes into a neutron. Let me use a whiteboard. So we have a proton changes into a neutron. Note that the mass number, what is the mass number? Is the number of protons plus the number of neutrons. So during beta decay, we have one proton changing into a neutron. So let's use an actual example. Let's say we had add a nuclide which had 20 protons and 20 neutrons. The mass number would be 40. Then it undergoes decay, beta decay, which results in a neutron changing into a proton. So one neutron is changing into a proton. So initially we had 20. So if one changes into a proton, how many will we remain with? We'll be remaining with 19. Then the neutron here has changed into a proton. Initially the number of protons was 20. So kama neutron moja imekuwa proton, how many protons will we now have? 21. What is 21 plus 19? It is equal to 40. Is your question answered?
Yes.
Thank you. Any other? I think we are now okay. Yeah, Levins?
In alpha decay, the helium, do you include the charge?
No, when writing the nuclear equation, we do not include the charge. We just write the atomic and mass number. If there's no other question, then we stop there. I'll send the assignment through your WhatsApp, through your class teachers. Thank you for attending the lesson.
Thanks for the lesson, teacher.
Thank you.
Thank you, William. Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Somebody was asking for definition of count rates. There you are.
Thank you so much, madam. Thank you, boys, for being well behaved. And we now break. Mathematics will be with Mr. Mbidi starting at exactly 11. Go and have a cup of tea. Thank you, guys.